Electronic transitions in hydrogen. Part A. The electron in a hydrogen atom makes a transition from the n equals 2 energy level to the ground level n equals 1 by the wavelength and frequency of the emitted photon. Now, the energy levels in the Bohr model for hydrogen atom is given by minus 13.606 divided by n square in electron volts. So using this we can calculate E1 to be minus 13.606 electron volts. That's the ground state energy. And the n equals 2 energy will be minus 13.606 divided by 2 square, which is 4. That gives us minus 3.4015 electron volts. Now if we calculate the difference between these two levels, n equals 2, n equals 1 to n equals 2, n equals 2 minus n equals 1, so we have a transition from n equals 2 to n equals 1. That is going to be equal to 10.2045 electron volts. And this must be equal to the energy of the photon emitted, hf, or h times the speed of light divided by its wavelength, hc over lambda. Now this formulation, when we have a delta E in electron volts, gives us for the wavelength, if we substitute the Planck's constant and the speed of light, one can show that this becomes 1240 electron volt nanometers divided by the delta E expressed in electron volts. So if we substitute these numbers here, we will find that the wavelength is 1240 divided by 10.2045, which gives us a wavelength of 122 nanometers. So that's the answer to part A of the question. Part B. In interstellar space, highly excited hydrogen atoms called Rydberg atoms have been observed. Find the wavelength to which radio astronomers must tune to detect signals from electrons dropping from the n equals 273 level to the n equals 272 level. So what is the energy of the 273 level? Energy of 273 level is minus 13.606 divided by 273 square, which is minus 1.8256 times 10 to minus 4 electron volts. How about the energy of the 272 level? That is minus 13.606 electron volts divided by 272 square, and that gives us minus 1.839 times 10 to minus 4 electron volts. The difference between these two, so if we have a transition from n equals 273 to n equals 272, that's what's happening here. The final energy is E272. The initial energy is E273. This gives us 1.345 times 10 to minus 6 electron volts. So that's going to be the energy of the photon emitted, which is hc over lambda. All right, so 272 level is more energetic, so absolute value of delta E will give us the energy of the photon emitted. And if we calculate the wavelength using our shortcut 1240 electron volt nanometers multiplied by delta E in electron volts 1.3545 10 to minus 6. This gives us a wavelength of 0.922 meters. Okay, so we make a transition from a higher energy level to a lower energy level, and therefore delta E will be actually negative here, so this is lower energy. But we see that the difference between the energy levels will be equal to the energy of the photon emitted in absolute value, so we can calculate lambda from our shortcut. Okay. In part A, we had a transition from n equals 2 to n equals 1. So the same thing is true here. N equals 2 has a higher energy. So this delta E absolute value is what we need, which gives us not E1 minus E2, which would be E final minus E initial, but E2 minus E1. So this is the absolute value of E272 minus 273. Now part C, what is the radius of the electron orbit for a Rydberg atom for which n equals 273? The radius of the orbit in Bohr model is n square multiplied with the Bohr radius A0. So that would be 273 square multiplied by 0.0529 nanometers Bohr radius. And that gives us, for the radius of the electron orbit, 3.94 micrometers. All right. Part D, how fast is the electron moving in a Rydberg atom for which n equals 273? Well, remember that we have uniform circular motion of the electron without radiation while in orbit. So we have ke square over r square. The Coulomb force equals to mass times the centripetal acceleration v square over r, which gives us, for the speed of the electron, ke square divided by mr, because we have a cancellation here, square root. That's how we calculate the speed. And if I substitute the numbers here, this would be Coulomb's constant 9 times 10 to 9, electron charge 1.6 10 to minus 19. Then I take the square, the mass 9.11 10 to minus 31, and the radius 3.94 10 to minus 6, all expressed in SI units. Then I take the square root. This gives me, for the speed of the electron, 8.31 times 10 to 3 meters per second. Part E, what if radiation from the Rydberg atom in part B is treated classically? What is the wavelength of the radiation emitted by the atom in the n equals 273 level? So instead of using the Bohr model, we are assuming that the radiation doesn't come from n equals 272 to n equals 272 level transitions. Instead, it comes from the classical radiation for the electron in orbit. So the period of the electron orbit is t, then 1 over t is the frequency, which is the speed v divided by 2 pi times the radius, because v is equal to 2 pi r, the circumference of the orbit, divided by the period. So if you substitute the speed that we have found in part D, 8.31 times 10 to 3 meters per second, divided by 2 pi times the radius, 3.94, 10 to minus 6 meters. This gives us 3.24, 10 to 8 hertz. And let's say that this is the source of the radiation, so that lambda is equal to C over F. C is equal to lambda F. 3 times 10 to 8 meters per second divided by the frequency we substitute 3.24 10 to 8 Hertz. This gives us a wavelength of 0.927 meters, which is very close to part B. Because in part B we found 0.922 meters. Now, why is this very close to the answer in part B? Due to Bohr's correspondence principle. Quantum physics agrees with classical physics when the difference between quantized levels becomes vanishingly small. So, for n equals 273 to 272, the difference between the energy levels is vanishingly small. Therefore, classical result will be approximately correct. So that basically tells us that this answer should be close to the quantum treatment. So in summary, we looked at electronic transitions in hydrogen. We calculate the energy for each level minus 13.606 divided by n squared in electron volts. We find the difference between the energy levels that corresponds to the energy of the emitted photon hc over lambda, and we have a shortcut to calculate lambda, 1240 electron volt nanometers divided by energy difference in electron volts. And for highly excited Rydberg atom, this energy difference that we calculate is quite small, and the corresponding wavelength using this formulation is very high. It's almost a kilometer. The radius of the electron orbit is found using n squared times a0, the Bohr radius, which is 0.0529 nanometers, and that gives us our answer 3.94 micrometers. The radius, how fast is the electron moving in the Rydberg atom, that we can calculate using the centripetal force of the Coulomb force, the attraction between the proton in the nucleus and the electron. And that gives us a speed of square root ke square over mr, which is 8.31 10 to 3 meters per second. And if we treat this electron classically in part E, this speed corresponds to a frequency, v is equal to 2 pi r times the frequency, 3.24 10 to 8 hertz. The wavelength is equal to c is equal to lambda f, or lambda is equal to c over f, and we get almost the same answer as in part B. So the classical radiation that would be emitted by this periodic motion of the electron is very similar to the wavelength of the radiation due to the transition from n equals 273 to 272, and that agrees well with Bohr's correspondence principle, because the difference between the energy levels 273 and 272 is very small.